In this problem, we have two very closely spaced lines, and we're thinking about how far away you could stand from these lines and still see them as two closely spaced lines as opposed to one single line. Now, I can't do this experiment very well from afar over the video because the resolution, which is what we're talking about here, depends on the resolution of your screen and of the camera, and so there are other factors involved. But you could easily try this at home. Take a ruler, make two lines that are 1 millimeter apart, and stand further and further back from those two lines until they blur into one. So you're taking it further and further away. And eventually you won't be able to distinguish them as two lines. You'll see them only as one line. And we can explain that using the theory of diffraction and this concept known as the Rayleigh criterion. Okay, so let's think about the diagram here first. On the left, we have an eye, right? So here's an eye. Here's the retina. And then here are two dots, essentially. So the dots are representing the two lines. The light from this one passes through the eye and lands on the retina. The light from this one passes through the eye and lands on the retina. But the pupil of the eye acts like a slit. And so light will diffract going through that opening. And the amount of diffraction will depend on the diameter of the pupil and the wavelength of the light. Okay. So these dots over here won't be perfectly encapsulated as images on the retina. They'll be slightly blurry because of the way that the light spreads and diffracts as it goes through the pupil. And if those two blurry spots touch, then your retina doesn't process that as two separate lines. It processes it as one line. Okay. And we're trying to figure out at what length away from your eye can you be when these two dots, these two blurry dots, touch one another. Okay, and that's what's given by this Rayleigh criterion. So the angle at which that happens, right, this critical angle at which the two dots become one, is 1.22 times the wavelength over d. It's important to note that the angle here given by this formula will be in radians. So use radians here. Either put it in as radians, or if you calculate it, know that it's coming out as radians. And lambda and d obviously are both distances. Make sure you have them in as the same units. All right, so I drew this with a blue pen. So my wavelength is the wavelength for blue light. The wavelength of blue light is about 470 nanometers. And I looked up the diameter of a pupil for an adult on average is about 3 millimeters. Obviously, your pupils dilate and contract based on the lighting conditions, but on average, it's about 3 millimeters. So if we take these rough estimates of numbers for what the wavelength of this color of light is and the diameter of a pupil, we can plug them into the Rayleigh criterion, and we find an answer of about 2 times 10 to the minus 4 radians. Okay. So I don't know about you, but that number doesn't mean very much to me. I don't think about things in radians. We can convert it to degrees, but more what we're looking for is how far away you can be and still see the two dots, or as it may be, the two lines. Okay, so then we take the angle and do a little geometry, and we can figure out the length away. And that length away will be the diameter of the pupil. Oh, sorry, wait, that's 10 to the minus 3. Oh, that's the 1 millimeter, 1 millimeter here. That's the distance that they are apart, not the diameter of the pupil. So you take the distance that the two things are apart and divide by this minimum angle at which you can see them in radians, and you get an answer of 5.26 meters. So in theory, I could be able to stand 5.26 meters away from this and just barely distinguish two lines. If I go a little bit farther, they'll blur into one, and as I move closer, I can more clearly see the two lines.